Okay, I think let's get started. So let me start with an announcement. We're going to have a picture taken after this talk. So at 11:30 in the courtyard, we'll take a picture so everyone should show up. And now it's a pleasure to introduce Pratik Rath, who's going to tell us about holographic reflected entropy and the entanglement wedge cross-section.
Thank you so much. Thank you so much to the organizers for organizing this lovely conference and workshop. It's been a pleasure seeing all of you in person. And also thank you for giving me the opportunity to present my work. The topic of my talk today will be, it's going to be sort of a summary of this research program that we've been pursuing with Chris, Tom, and a student at UAUC, Simon Lin. It's resulted in 2 of these papers and some more work that's to appear. I should point out that Simon is a graduating student this year, so look out for him when he applies for postdocs. And for people who've heard some version of this talk, hopefully there'll be something new, which are like these results which haven't appeared yet. And for people who haven't kept track of this, hopefully this will be a useful summary of what we've achieved and what we still don't understand. All right. So let me start with some motivation. The reflected entropy and entanglement wedge cross-section duality, I think of largely as a generalization of the Ryutake-Nagy formula. The Ryutake-Nagy formula happened many years back, led to a lot of progress. And it's sort of the main thing in this motivation to understand geometry from entanglement. And we haven't gone much beyond entanglement entropy ever since. So it's kind of useful to understand other entanglement measures and how they could be geometric, and the reflected entropy and the entanglement wedge cross-section duality is one such example where there's a nice geometric dual for this quantity, and it helps probe deeper in both senses, in the geometry and entanglement. It's a particularly nice multi-party entanglement measure. It's an easy thing to compute, and it so happens to have a nice geometric dual. Typically, entanglement measures are pretty complicated. Like the quantum information community struggles with this a lot. Like even classifying tripartite entanglement for 3 qubits was a big deal. So it's clearly a hard problem. And so it's useful when we can use geometry to learn something about entanglement and vice versa. And so that's part of the motivation here, to extract some useful entanglement measures, which are the relevant ones in this understanding of geometry from entanglement. Another advantage, which I guess has recently become kind of popular, is that the reflected entropy is something that's well defined in quantum field theories itself. So there's been a lot of discussions about von Neumann algebras and how that's how we should think about things, and it gives us new techniques to learn things. And this is sort of a rigorous way of understanding entropy in quantum field theories. And more so, what I'm going to talk about here is largely going to use toy models to understand this problem, like away from ADS-CFT, but like toy models of ADS-CFT that are kind of accurate in some ways. And so the techniques that we use here are pretty widely applicable. Like the models I'll use will be tensor networks and simple models like JT gravity, which teach us new things about the replica trick. Like the replica trick is a difficult thing in general, and it's hard to deal with except in simple situations. And so hopefully this teaches us some new things about analytic continuation and subtleties that can arise in the replica trick, which could have lessons in general for ADS-CFT. So that's sort of broadly my motivation. Okay, so let me start by reviewing what the reflected entropy is. It's proposed in this paper by Tom and Shovik Datta. So given any density matrix on 2 systems, A and B, one can perform a canonical purification. So the canonical purification is just taking the density matrix, taking the square root of it, and interpreting it as a state. This is something pretty familiar to us. We go from the thermal state to the thermofield double. And this is just a generalization of that to bipartite density matrices on arbitrary Hilbert space of A and B. And so this state lives on a doubled version of the Hilbert space where you have the original A and B, but also two copies A star and B star, which you should think of as the reflected copies of the systems A and B. Once you do that, then the reflected entropy is defined as the entropy of the regions A star in this particular state. So a picture to have in mind is you start with a density matrix on these two systems, and you reflect by doing this doubling, and then just compute the entropy across this cut. So there was some sort of entanglement between A and B. When you purify it, there's still some entanglement across this cut between these two systems, A star and B star. And so the reflected entropy is measuring some sort of correlation between A and B that existed in the original state. Okay. So just as a side comment, like this is well defined even in algebraic QFT, because it sort of generalizes naturally to what's called the split entropy. So whenever you have two subregions A and B which are separated from each other, quantum field theory has this nice property, which essentially you can think of as locality, which is that when you have two of these subregions, you can, with some gap in between, then you can sort of you can find an algebra, which is so typically subregions in quantum field theory have type 3 algebras for which you can't associate entropies. But what you can do is you can look at the algebra of A and the algebra of B prime, where B is the other system, and you can find something, find an algebra which is type 1 that lies in between them. So it's sort of nested between them. In general, there's many different such factors, but the canonical purification motivates a specific such factor. And since it's a type 1 factor, you can rigorously assign an entropy to it, which is now well defined in the continuum limit. So this is some concrete way in which you can understand an entropy even in the continuum limit. Okay, good. So let me just briefly mention what the important properties are and why it's useful as an entanglement measure. One of the most important things that I'll talk about is that the reflected entropy, the difference between the reflected entropy and the mutual information between two systems, both of which are some correlation measures, can be written as a conditional mutual information. So it's a conditional mutual information between A and B star given B, which should roughly be thought of as measuring the correlations between A and B star, which are sort of invisible to B. So if all the correlations between A and B star are sort of mediated by B, then the conditional mutual information vanishes. And the Markov gap, which is the difference between these two, is a measure of that correlation. Just because it's a conditional mutual information, you can show that it's positive. But interestingly, in holography, we often find that it's a large amount. So it could be that the entanglement wedge cross section. If you believe the entanglement wedge cross section proposal, this difference can be an order 1 over G amount, and so it can tell you about a large amount of correlation between A and B star that's invisible to B. What does that mean? The easiest way in which I think about it is it's some kind of measure of tripartite entanglement. So suppose you had some state, let's say it's a 3-party state between A, B, and C, and it had mostly bipartite entanglement. So it had some entanglement structure, which was bell pairs shared between A and C, A and B and C. And perhaps you can have some direct sum over such states. Then you can show that the canonical purification takes this particular form where it's now a 4-party state where the correlations between A and A star come from the ones between A and C. The ones between B and B star comes from the one between B and C. And the correlations between A and B are preserved as they were. In this picture, it's quite clear that the correlations between A and B star are mediated via B. So there's no conditional mutual information, and so every bipartite state would have 0 Markov gap. So the existence of this Markov gap tells you that there should be some sort of tripartite entanglement structure. There should be some non-trivial kind of entanglement. And this is interesting in holography because for a while, people thought that maybe motivated by some answers from bit threads, people thought that it could be possible that bipartite entanglement is all that you care about in holography. And that's a pretty simple entanglement structure. And perhaps that would help us understand geometry pretty easily. But the existence of this Markov gap sort of rules that out and says that tripartite entanglement is pretty important for holography. More so, the reflected entropy satisfies this continuity bound, which says that if you change the state a little bit, if you tweak it a little bit, the reflected entropy doesn't change much. And so it's a sort of useful measure of entanglement. It's more like the entanglement entropy, which doesn't change much when you change the state. And so you can assign some nice geometric meaning to it. And I should mention that there's a caveat in all of this, which is there's a technical condition you need for something to be a correlation measure, which is that the correlations measured by the reflected entropy between A and B should be strictly larger than, did I mess that up? I think it's the opposite way, sorry. It should be strictly smaller than the correlations between A and BC. Basically, when you remove C, the correlations should only go down. This is something that hasn't been proven yet. So technically, this doesn't count as a correlation measure as of now, although there's no counter examples to this statement. So perhaps it could be proved. And this is just an advertisement that the reflected entropy hasn't been worked on much by the quantum information community. I think it's a useful quantity that should be looked at much more, and just from a QI perspective. But one thing that I can say about this is that assuming assuming the holographic proposal, you can show this property. And so at least holographically, it seems to be true. And so, and there's been no counterexamples in any other situations. Yeah.
So just wondering, so you call this a reflected entropy entanglement measure?
Yes.
So you have this inequality which says it's larger than the mutual information.
Yes.
But on the other hand, we know sort of mutual information can be positive if you just have classical correlation.
Yeah. Yeah.
So this reflected entropy will also be positive if you just have no entanglement but classical correlation.
Yes,
right?
That's right.
Would that bother you?
I mean, it does, you're right, that it captures both classical and quantum correlations, but it does so in a way that's different than how the mutual information does. So, I mean, it's not that it's not, I guess it's called a faithful measure or something like, it doesn't vanish when there's no entanglement, but like you could have like GHZ states where the reflected entropy is equal to the mutual information. But I think it's still like finding something about the entanglement structure that's different from the mutual information. So it's useful in that sense.
Okay, yeah, thanks.
Yeah. All right. Okay, so what's the holographic proposal? The proposal is pretty simple. The reflected entropy is related to the entanglement wedge cross section. It's twice the entanglement wedge cross section in units in Planck units. And the picture you should have in mind is, let's say you have two of these regions, A and B, and they're in a connected entanglement wedge phase. Then the cross section is the minimal area surface that splits this entanglement wedge into two portions. One that's homologous to A and one that's homologous to B. And in the disconnected phase, there's no need to split the homology regions into two parts. So the reflected entropy vanishes, whereas it's some order 1/g amount in the connected phase. There's a similar proposal that was made for the entanglement of purification earlier. The entanglement of purification is also a nice entanglement measure, but it's something that's hard to compute. It requires like optimizing over all possible purification. So it's hard to get a handle on it. However, it's still plausible that the entanglement purification is also related to the entanglement wedge cross section. So it would be nice to understand in any controlled setting, whether it's in any way related to the entanglement of purification. But the reflector entropy here has the advantage that we can compute it in particular models, like we can really show that this is the case. So, good. So the basic arguments for this proposal are the following. The first sanity check is to just check that it satisfies all the same inequalities. Whatever inequalities you could prove for the reflected entropy hold for the entanglement wedge cross sections. That's sort of straightforward. And you can try to argue that a way to motivate this proposal is that there's a plausible geometry for the canonical purification. So we know that the system A and B is dual to the entanglement wedge, this blue region. And by this canonical purification, all we're doing is doubling the system in a very symmetric way. And so a natural saddle that you could consider is to just take 2 copies of this and then glue them at these extremal surfaces. That gives you some kind of cylinder-like geometry where the entanglement wedge cross section, or more so 2 copies of the entanglement wedge cross section, are the throat of the cylinder. And so if you now assume that this is the geometry and you can apply the Ryuta-Kinagi formula, then the entropy of these systems is given by the size of the throat, which is twice the entanglement wedge cross section. All right. But there's some issues with this argument. And the issue is, in order to derive something like this, the only way we really need to, the only way we really know how to do this is to do a replica trick. So the replica trick that one can do to compute such a quantity in holography is to consider a 2-parameter generalization of the reflected entropy, which you should think of as the nth Renyi entropy, the usual Renyi entropy of a state that's a generalization of the canonical purification. So it's rho to the m over 2, where m is taken to be an even integer. If m is taken to be an even integer, this can be prepared by a replica trick, and the nth Renyi entropy for integer n can also be computed. And so there's a well-defined path integral that computes the mn version of the reflected entropy. You can do that and then try to argue by some Lukowitz-Maldacena type argument that the entanglement wedge cross section comes out of this calculation. And the picture is as follows. If you want to prepare, so this boundary computes trace rho to the m, where each of these is a copy of, you should think of as a copy of rho. You can cut this open in the middle to prepare the state rho to the m over 2. And that's true for even integer m, but now you can try to do this quotienting like Lukowitz-Maldacena and think about instead the state that's prepared on these slices, which is essentially, it just has the original boundary conditions and it has some particular opening angle. And so now it's something that's analytic in M, which you can then analytically continue. When you do that, you find this geometry. So it adds to the plausibility argument that this really is the geometry for the canonical purification. And then if you can use the RT formula here, then you're done. But there's an issue, which is that this calculation, when you try to do the replica trick to compute the Renyi entropy, there are phase transitions when you're trying to do this analytic continuation. And which way you do the analytic continuation matters. So we eventually want to analytically continue both m and n to 1. Whereas the problem is, depending on how you do that, whether you do it, whether you take m to 1 first or n to 1 first, the answer changes. And so there's a subtlety in this analytic continuation, which is a little hard to understand. And so you might worry that there are important effects coming from perhaps other saddles that might change the answer, and it needs to be more carefully checked. And so what I'll be telling you largely today is that this issue also arises in a lot of toy models, and there we can really understand why this issue shows up. And briefly, the issue would be that we're sort of considering a limited class of saddles, and there's more saddles that we should really be considering. Once you consider those new saddles, this issue can be resolved. More so, there's another issue with the reflected entropy, which is that it has a discontinuous phase transition. So the mutual information phase transition is a continuous one. And in this case, however, when you jump from the disconnected phase to the connected phase, the reflected entropy suddenly jumps from 0 to a order 1 over g amount. So that's a pretty sharp transition. And you might worry that non-perturbative effects might become important in that region and change the answer significantly near the phase transition. So this is another thing that we were interested in understanding in particular toy models. All right. There are various generalizations to this, which is you can add in time dependence, you basically do maxi-min, and it pretty much works in the same way. It reproduces all of the inequalities. You can include quantum corrections, the only subtlety being that the cylinder geometry was generated by gluing together at extremal surfaces. When you do that, you satisfy the constraint equation, so that gives you reasonable initial data to generate a space-time. When you do this about the quantum extremal surface, there's instead going to be shock waves, because the location of the location at which you're gluing is not extremal, but then the shock waves from the matter sort of work out correctly, so that this still satisfies the constraint equations, and you get a reasonable geometry, which was worked out in some detail in this paper. And more so, the same story holds when you look at islands. So in this picture, I have the West Coast model with where you have radiation systems R1 and R2 that are purifying the radiation in the interior. And when you do the canonical purification in the connected phase, the picture is that of R1 and R2 being entangled with their reflected copies R1 star and R2 star via this closed universe. So it's sort of it's a controlled place where we have access to a closed universe, and perhaps we could use this to learn something about closed universe in the setting of ADS-CFT. Right. Okay. So with that, let me talk about the actual calculations that we'll end up doing. Largely, all of the calculations will be in tensor networks, in particular random tensor networks, which is a good toy model because it has this structure that's quite similar to the gravitational path integral. There's a very precise match between the gravitational path integral in what are called fixed area states and the calculation that one does in the random tensor network. And all the same issues will arise there. So if we can figure out how the issues are resolved in the random tensor network, it sort of helps us understand what happens in ADS-CFT more generally. So just briefly, the map between these random tensor networks and the path integral is that, as you expect, the network is dual to some sort of spatial geometry on some spatial slice. And the interesting thing in which the random tensor network reproduces features of the path integral is that when you do a replica trick, you take multiple copies of this tensor network and try to compute something like the Renyi entropy or any such object. The calculation, when you do this Haar averaging over random tensors, becomes effectively a sum over permutation. So it's a sum over different permutations that are applied on these tensors. And this nicely matches with the sum over topologies that you find in the replica trick. So for example, if you compute something like the third Renyi entropy in a fixed area state where you fix the area of the extremal surface, allowing for an opening angle. And one possible geometry that contributes to this is the one where you cyclically glue these Pac-Man-like geometries. And there's a one-to-one correspondence between this, between the action that you get from this gravitational calculation and the calculation in the tensor network, where there's where the same action is reproduced by a permutation, which is just the cyclic permutation. So more precisely, you can always like assign a permutation to any of these geometries that you get from gluing together these fixed area geometries. All right. So just in general, let me just say that tensor networks reproduce some features of holography pretty accurately, and it's probably more accurately than we should have expected. And in particular, it's because of the fact that this sum over permutations is exactly analogous to the sum over topologies, that some of the topological aspects of gravity are pretty much reproduced by the tensor network. And it's interesting because phase transitions in quantities are often controlled by these non-perturbative effects, which come from like other topologies. So the tensor network is pretty useful when you want to learn about such non-perturbative effects, and it's an easy playground where you can figure them out. More so, there's always this issue with the gravitational path integral that we don't really know what to sum over. There's issues with the contour and so on. I mean, it's something that's not a very controlled approximation. And the tensor network, on the other hand, is something where you exactly understand what needs to be summed over. So it's a much more controlled place where you can really trust the answers you obtain. Very often, because of this match between the tensor network and the path integral, you find features in gravity that you would have never expected. For example, a nice example of this is the subleading Weingartens by Douglas Stanford and collaborators, which is where it's a very trivial calculation from the perspective of the random unitaries, but in gravity, it's a pretty non-trivial calculation which tells us about chaos and so on. It's something that you would have not thought of finding, but once you look at the calculation with random unitaries and trust it fully, you look for it in gravity and you find it. And there's many other examples of this. There's other things like entanglement phase transitions and so on, where the exact same structure shows up in both tensor networks and the path integral. So I'd like to take it maximally seriously and see what we can learn from it. And also, it's a playground where a lot of things have been figured out. People have worked with random tensors a lot. There's a lot of different techniques, some of which we heard during this workshop as well. There's free probability theory. There's numerical things you can do with it. So there's many different ways in which you can attack the problem compared to what we can do with the path integral, where we have much more limited capacity. And so it's a useful model. There's still some cons with the tensor network because it doesn't capture everything about gravity, right? Like it doesn't have features like back reaction. For example, here, once you have fixed area, then the saddle doesn't change when you glue things together. Whereas when you don't fix the area, like in gravity, we know that the solution changes every time we compute something like the Renyi entropy. This is a feature that the tensor network misses. And so some local dynamics are missing, but it still captures some broad topological features. Similarly, there's another feature which the tensor network has, which is it can simultaneously fix the areas of all surfaces. Whereas this is something you cannot do in gravity. You can't, areas corresponding to the HRT areas for crossing regions are typically non-commuting. They are time-like separated, and you can't simultaneously fix all of them. So there are issues with the tensor network, and you should be careful when applying it to gravity, but still there's a lot of things that it can teach us. And there's still an open question about how random a tensor network needs to be able to reproduce features of gravity. The simplest model to work with is just the random tensor network, where you have a completely hard random tensor. But typically in quantum information, people deal with things what are called K designs, so something which can reproduce up to K moments of the random of a Haar average. And it's not completely clear how random we should think of these tensor networks when modeling gravity. Yeah.
I think the optimal path is difficult. I had a question. So when you said there's a problem of basically no local dynamics in the tensor networks, and there's no commutativity, the fixed area state story, how much are those effects do you think of the large N limit also large bond dimension limits that you're considering in random tensor networks. Because you sort of go away from infinite n, I mean, then you would expect somehow that your gravitational dual has well, non-zero Gn. So that limit, you would expect to see these effects, no?
If I understand correctly, I mean, even in the G goes to 0 limit, like let's say you compute like the third Renyi entropy or something, the saddle point that you get in gravity is totally different from just gluing these together, because when you glue these together, there's a conical excess at the location of the extremal surface if you naively take this, so it doesn't solve Einstein's equations. And so even in the G goes to, in the classical limit, like you find something that's different. So there's some effects of back reaction when you want to compute complicated things like the Renyi entropy, like which has some non-trivial back reaction, unlike the entanglement entropy. So I mean, the G goes to zero limit is analogous to the large bond dimension limit in the tensor network.
I see, but these like called them Weingarten corrections don't solve any of this.
No,
okay.
Yeah. I guess what you mean by Weingarten corrections is like the other permutations and so on.
Yeah, the subleading corrections, exactly. Like
Yeah. So the other permutations also have like analogs with like fixed area geometries, and they're typically like non-perturbatively suppressed. So they don't change this effect. Like this is something that the tensor network really misses.
I see. Thank you.
Yeah. All right. Okay. So now let me get to the part where I discuss like the stuff that we did. So in random tensor networks, we tried to attack the same problem of understanding reflected entropy with this replica trick where we compute trace rho to the n for this purification, which was rho to the m over 2, again taking n to be integer and m to be even integer. This, as I said, was computed by some sum over permutations with given boundary conditions. The boundary conditions are essentially fixed by the twist operators that you need to apply to do this calculation. And we're applying 3 different kind of twist operators here. On the region, which is the complement of AB, we're just tracing out the region. So that corresponds to like applying the identity permutation. On the other hand, in the other regions, we want to prepare this state rho to the m over 2. So the picture I have for that is we have these circles which have m boundaries, and there's n such circles. So in this case, I guess m is 6 and n is 3. And what we want to do is compute the powers of the density matrix rho to the m over 2, which basically says you want to cyclically glue each of these circles to perform this this power. And further, in order to compute trace rho AA star to the n, you want to apply another twist operator that that permutes some of these copies. For example, on the A system, you want to permute the n different copies of these, so that computes the trace rho to the n part of it. These are some particular boundary conditions that you can apply, and the structure of the permutation group helps you sort of classify it. So there's a distance measure that you can have on the set of permutations, which is called the Cayley distance. The Cayley distance is essentially the number of swaps that you need to go from any particular permutation to another one, and so you can sort of classify the relevant permutations by looking at the structure of the Cayley diagram. And the structure is as follows. So the important elements that we have on the boundaries are these E, GA, and GB. And there are some geodesics which go from E to GA, E to GB, and so on, which are essentially the distance minimizing roots in this Cayley distance measure. And there's a particular element X, which is a very symmetric element. It just corresponds to gluing each of these m over 2 copies with themselves, which sort of lies at the junction point. So if you look at a geodesic going from the identity to either GA or GB, it sort of follows the same route all the way until this X, where it splits into these 2 parts, one which goes to GA and one which goes to GB. And there's separately some other geodesic that goes between GA and GB. So it's sort of a non-trivial phase diagram for these permutations. But it just turns out that in the end, these are the only important permutations. So these 4 permutations are the only ones that are ever important in looking at what's the dominant contribution. When you're near phase transitions, you need to be a little more careful. Things that are on the geodesic sort of become degenerate, and so you need to resum over all of those contributions. But away from phase transitions, these are all the permutations that matter. Note that in the gravity calculation, the argument that was being used depended on using these GA, GB, and E type gluings. So the gluings that were motivated by this Engelhardt wall construction and so on were only this limited class of saddles. And there was no analog of this X saddle, which came from understanding what the geodesics in this permutation group are. And this XX is precisely the saddle that we needed in order to fix the issue. So once you add in this X, we see that the order of limits issue gets fixed, and it's something that's important in gravity. So the tensor network sort of teaches us about a saddle that was relevant in gravity that we had completely missed. As I said, the general structure is that it's just these 4 permutations that are relevant. And what it looks like is the following. So if you have C, for simplicity, I've just drawn A and B as connected, but you could have them being disconnected and so on. There's the phase structure is as follows. The identity acts on C, and so there's a domain attached to C where the identity, where the tensors permute via the identity. Similarly, there's a domain of GA anchored to A, GB anchored to B, and there's some tension between them. But more so, there's this X saddle that shows up in between. So this X sort of marks this region in between all of these surfaces. And there's some tensions you can assign to each of these domain walls, which comes from essentially the distance, the Cayley distance on the metric, on the Cayley metric. And yeah. Oh, sorry. Yeah, that's a good question. So it's actually, oh, sorry. So the question was whether this X breaks replica symmetry. It's not exactly, I mean, if anything, if I just go back to this picture, it's more symmetric than either GB or GA. So I don't know if there's a sense in which it breaks replica symmetry. It's just a different saddle from what had been considered before. There are other instances, like for example, in the entanglement negativity, where replica symmetry breaking saddles become important, but I don't think there's a sense in which this is replica symmetry breaking. Okay. Okay, good. So in the end, this is what it comes down to. So first you work hard, look at all the permutations, show that this is all that ever matters. And then you have a simple picture for what the phase structure is like. Essentially, firstly, the tensions here are n and 2 times n minus 1. So there's no m dependence. So firstly, the analytic continuation in m is rather simple. You can just compute the reflected entropy by, it's just a simple function of the domain walls here, which is this minimal surface, and this sort of junction, which we call the tri-way cut. And the tri-way cut is essentially now, it's some generalization of the minimal surface where you assign different tensions to each of these 3 portions, which meet at one point in the bulk. So it's sort of a heuristic picture, is that this tri-way cut is now measuring some kind of tripartite entanglement. Like when we had these single domain walls, they were measuring some kind of bipartite entanglement, for example, for the entanglement entropy. And this tri-way cut is becoming important in the reflected entropy, is some sort of heuristic way of understanding that tripartite entanglement is becoming important. Since there's no m dependence, it's sort of relatively easier to analytically continue in m, whereas as you change n, because these tensions are different, the locations of these surfaces change. And you could think of this as analytic in n, although it's sort of hard to rigorously prove that. But if you think of it as analytic in n, then you see that as you take n to 1, the tension here vanishes. And so this just becomes like a probe, whereas these have some finite tension. And so essentially what happens is that this this tri-Weikart gets pulled towards the minimal surface, and you end up again with the answer that's twice the cross section. So this is sort of some more rigorous way in which you can show that the reflected entropy really is twice the cross section. Yeah.
Should I think of this tri-way cut as also having some kind of tension in itself? Like if I was doing a thin wall calculation in gravity,
Yeah.
and I had domain walls meeting at higher codimension domain walls, they would
Yes.
also have their own tension. So is there a tension for the tri-way cut point?
I don't.
You mean for the point itself?
Yeah,
Is
for
that
the point
question?
itself. I don't think so. I think all you do is you assign some, no, at least here, there's no analog of that. The tensor network is sort of a dumb version of gravity, right? Like this point is that its meeting is not like, it doesn't have its dynamics or anything. All it's doing is like, there's some tensors here, wherever they are, like some discretized version, and it's just splitting them into these 3 different domains. This junction point doesn't really have any geometry associated to it or anything like that.
Yeah, in a general network, which this applies to, it's not even clear you can define that point.
Yeah. All right. Okay. One interesting thing that came out of this is there was this, initially I mentioned that there was this mostly bipartite conjecture that was motivated by bit threads. And particularly it was so because bit threads seem to have this configuration where you had bipartite entanglement, like flows between A and B and C and A, which could give you all the correct entropies. But in this picture, we see that, and we already saw that the existence of this Markov gap ruled out bipartite entanglement. But here, there's sort of a more direct connection in the tensor networks. And it's just the fact that when you think about the problem that we had here, which was just trying to minimize the action given the existence of this tri-Weikart and the minimal surface, you can reformulate all of that in terms of an integer program. So you can think of it as a flow, you can think of it as a program where you minimize this quantity, which is essentially like the cost of the domain wall, which is weighted by the bond dimensions of the network. And there's some constraints on it, but the important constraint on the program is that this domain wall, the thing that calculates the cost of the domain wall, is an integer, which essentially says that when you go from either A to C or B to A to B or whichever way you want, when you cross a domain wall, it's an integer. There's an integer number of domain walls that you cross. You can't cross a half integer domain wall. Once you formulate it this way, it sort of becomes clear that it's now difficult to find any bit threads picture. The reason is, typically when you have something like min cut, you can dualize and find something like max flow. There's a natural connection between them, but that's only after you restrict, or after you relax this integer constraint. So if you were to relax the integer constraint and then allow rho to be any real number, then you'd find that the minimal energy configuration is actually of the following form, where the tri-Weikart, which was here, gets pulled apart into these minimal surfaces. This is precisely the picture that the bit thread suggested to us. So the bit threads had exactly this picture where the domain walls were at the minimal surfaces, and hence naturally it gave something that was a linear combination of them, which was the mutual information. And so this integer constraint is super important. So if you were to do the analogous computation for entanglement entropy, there is no difference between whether you keep the integer constraint or relax the integer constraint. But once you do the reflected entropy, this tri-Weikart seems to have some non-trivial integer constraint. The difference between the energy configuration when you keep the integer constraint and relax it is what's called the integrality gap. When you have an integrality gap, it's like it's typically an NP hard, I think, problem to solve this program. Whereas once you relax the integer constraint, it's just a flow problem, which is simple to solve. So there's a big computational gap between solving these two programs. And it seems like here, there's a sense in which gravity is, or like tensor networks have this, it's super important for the reflected entropy that they have this integrality gap, which is heuristically related to the Markov gap that we talked about before. The difference between the reflected entropy and the mutual information was this Markov gap, and it comes from the existence of this integrality gap in the tensor network. There's probably some deeper connection to that, but at this point, that's where we are. So once you have that, you can essentially do this analytic continuation. It gives you twice the cross section. But there's some issues with proving it rigorously, but at least for some simple class of networks, such as like one tensor, which is just a random tripartite state, you can do a lot of things. You can do things like prove rigorous bounds, which allow you to believe that the analytic continuation is correct. There's also resolvent type calculations you can do, where you resum all of the moments of the density matrix, get some spectrum, and compute the reflected entropy. And also there's like numerical checks that you can do with these small tensor networks, all of which gives this consistent story. So it sort of adds a lot of evidence to the kind of analytic continuation. And so the proposal in the end is that the correct order of limits for this problem is to analytically continue to n equals 1, which is where you compute the entropy. Do this for m, which is greater than or equal to 2. The m greater than or equal to 2 comes from the fact that the tension between this x element and E was proportional to m minus 2. And this answer, heuristically, what's happening is the tension in the bulk is becoming negative, and you shouldn't trust that answer. So stay in a regime where the tensions are positive, perform this analytic continuation, eventually take m to 1 from that answer, and that gives you the correct answer. This is precisely, in the end, this is precisely what was done in the ADS-CFT case. And so it seems like it's consistent with that answer, but there's a lot more evidence that we can find from tensor networks. Okay, good. So let me just briefly tell you about the resolvent calculation and what happens near the phase transition. All of this was largely away from the phase transition. Near the phase transition, a picture that I have for this is, so let's take a simple example, which is a 3-boundary wormhole where you have these throats. This is roughly what is modeled by a single tensor network with 3 legs. This the tensor network can be thought of in gravity as preparing this fixed area state, where you fix the areas of the different extremal surfaces, allowing for conical defects in the bulk. And then what you want to do is look at the state, which was this rho to the m over 2. Similar to what Ahmed was saying, you can consider the norm of the state and look at the Z2 symmetric slice. It turns out that the different kinds of diagrams that you get are essentially classified by how many permutations cross this middle line. And the picture that arises from that is the following. So there's different kinds of diagrams that you get from this purification. There's a diagram where you just get the disconnected purification. So if you were in the disconnected phase for AB, which is where the extremal surface was just the union of these two surfaces, you would just take these 2 copies, glue A to A star and B to B star. There was no connection between them. And so you just get these two boundary wormholes. But then there's a connected phase where the minimal surface is this connected one, which is gamma C. And then when you glue them together, you get something which is a 4-boundary wormhole, which has a non-trivial entropy when you compute the entropy for AA star, and that's basically twice the cross section. These were the 2 saddles that were considered in ADS-CFT, but there's actually more analogs to these saddles. You can also have 4-boundary wormholes which have a genus. So you can take 2 copies of this, glue them together at the extremal surfaces, and you end up with a 4-boundary wormhole with a handle. This handle basically now tells you that the entropy of AA star is given by 4 copies of the cross section, and so the entropy is 4 times EW. And in fact, there's an infinite series of this. When you analytically continue in M, you find an infinite class of these geometries, each of which are labeled by an even integer times the cross section. So they have an entropy that's twice or 4 times or 6 times and so on. So you can check this with a resolvent calculation or numerical checks, and there's essentially 2 situations. One where the cross section itself is the minimum of the 2 throats, which is then nicely modeled by this single tensor network, which then has a disconnected phase, and all of the other higher genus surfaces just have a cross section that's given by the union of these 2 throats. So you get 2 peaks, one for the disconnected phase and one for the connected phase. And on the other hand, if you have another cross section here in the middle, which is the minimum one, then you can really see the difference between all of these different saddles, and you find a spectrum where there's a disconnected phase, there's a connected phase with 2 EW, but then there's also this whole sequence of 4 EW, 6 EW, and so on. And this is something you can just check numerically as well, and has this nice structure. So it seems like there's a very rich structure to the tensor network when you do this canonical purification. As we saw before, like when we are away from phase transitions, the answer is twice the cross section, and these other higher genus saddles only really become important near the phase transition, but you can resolve the phase transition using that. So when you look at the phase transition, you see that in the microcanonical ensemble, which is what the random tensor network really computes, there's a sharp transition which you can resolve using some resummation. And there's a very similar model to the tensor network, which is this PSSY model, which essentially is, I mean, you can essentially think of it as a random tensor network with some fluctuations in the area. And when you do that, you find that the transition is a little more smooth. There's a wide window here of order 1 over square root g, where the transition happens. This is similar to what happens for the entanglement entropy as well. Like it's something that comes from just the area fluctuations near the transition. And quite interestingly, this plot is identical to the one for the PETS map. So if you look at the fidelity of the fidelity of the PETS map, which succeeds in the connected phase and fails in the disconnected phase, even near the phase transition, the reflected entropy sort of tracks that exact same probability. And perhaps there's a deeper connection to the PETS map, which we don't know yet, which arises from understanding the reflected entropy in terms of some reconstruction map. So this was for a simple network. For a more general network where you have these non-trivial tri-way cuts, effectively what you get is that the state is a superposition now over different values of the cross section. You can have these X regions which pinch the cross section, and so there's a non-trivial tri-way cut, and you sort of have a sum over different values of the cross section. Which is more of a geometric effect. The previous thing that we saw was a sort of topological effect where you had different peaks labeled by the genus. And now it's sort of, we have different portions of the spectrum that are labeled more so by the size of the cross section. So it's sort of a more geometric effect, which might be interesting to study in ADS-CFT. So just because you have a sum over all of these different areas, you see that the spectrum of areas, once you do the canonical purification in a tensor network, is non-trivial. The random tensor network itself had this dumb spectrum where it was just a flat spectrum. It just had one peak, but you get a much richer structure once you do the canonical purification. All right, so with that, let me summarize. What I try to argue in this talk is that there's a lot of evidence for this holographic proposal of the reflected entropy being equal to twice the cross section. And so the tensor network sort of taught us some new things about the ADS-CFT. We found new saddles. We saw how phase transitions can get resolved, etc. And in general, the random tensor network has a rich structure that guides us to such new results, which could be exploited more to understand other entanglement measures or so forth. Okay, so thanks.
Further questions for Pratik?
Oh. How do I? Maybe I should address that first. So the question here was like the reflected entropy is defined by doing the canonical purification and then computing the entropy. This is true. I mean, in a finite system, there should be no order of limits issue. If you can do this calculation perfectly, there shouldn't be an order of limits issue, and you should just you can do whatever continuation, and it should be fine. This issue essentially arises because you're working in the saddle point approximation. You want to work in the G goes to 0 limit and compute these classical saddles, and then it's not obvious what's the right order of limits. So yeah.
So as you also mentioned at a certain point, another known measure for correlation in mixed states is negativity.
Yeah.
So can you comment about relations or differences between reflected entropy and negativity? Like, for instance, in which sense the correlations that are captured by these two quantities are different?
Yeah, that's a good point. No, actually. So the negativity has been studied a lot more in the quantum information literature. So we kind of understand that there's some distillable entanglement that it captures, and there's some bound entanglement that's not, and so on. But for the reflected entropy, I think we don't completely understand exactly what kind of correlation it captures. Yeah, I don't have much better than that.
More questions? Okay, if not, let's thank Pratik again.
Thanks.